right, so what we're going to be discussing today is Algorand smart contracts. The title, we also said we would discuss smart signatures. Smart contracts and smart signatures are written in the same language. Smart contracts happen to be the one that we're going to focus on in this particular talk because they are the ones that are most used by app developers, specifically for blockchains. So as a way of agenda for this talk, the three things that I'm going to try to cover is give you an overview of what a smart contract is and what it is on, what a smart contract is on Algorand. And then I'm going to discuss the language you write these smart contracts in, and it's called Transaction Execution and Approval Language. We just call it TEAL. So in the TEAL language, and as part of that, some of this will be low-level assembler-like language. So in addition to that, I'm also going to explain how you can develop those smart contracts in Python. And so those are the three main subjects I'm going to try to cover today. So to start off with, what is a smart contract? Well, a smart contract is just a small piece of logic that you write in a development environment and you deploy to the Algorand blockchain. And it just lives in the blockchain forever unless you delete it. Now you initiate this bit of logic to run with what we call an application transaction. So you send an application transaction to the Algorand blockchain, it fires up your code, runs your code, has access to the ledger and makes decisions. And its sole job is to return true or false. That's the main job of a smart contract. It either approves, and if it fails, it fails the actual application transaction that you send to it. If it returns true, any changes done in the smart contract to the ledger take effect. That's essentially how smart contracts work on Algorand. But what's interesting about these is Algorand has six transaction types, and these include things like payment transactions, asset transactions, asset transfer transaction, creation transactions. So we have a whole set of transaction types. The application transaction happens to be a very special one that allows you to trigger a smart contract. So one thing that can happen, we have this feature at Algorand called atomic transfers, where you can send up to 16 transactions at once. And if any one of the transactions in the list fail, they all fail. So this allows you to group a smart contract call with like a payment transaction. And if the smart contract fails, then it will automatically fail the payment transaction as well. So that's a common feature we use in development when you're developing apps that are based on smart contracts, is you group those transactions. And if the smart contract fails, then the payment transaction or some other transaction in the list will fail. So the whole idea is you deploy this contract out on the blockchain, and this is where it lives. Now, you can write, when these contracts are deployed to the Algorand blockchain, they're actually deployed as a piece of TEAL code, and we'll get into what that means later in the talk. But it's important to note, while you're in development environment, you can actually write these in Python. Okay, so let's say I have my set of smart contracts living out, on the Algorand blockchain. I initiate one of those by sending an application transaction to the Algorand blockchain. It will fire the logic, run the logic, and what it'll do is the contract logic can read data from the ledger. It can read the transaction data, any transaction information passed in with the transaction, and it makes a decision. And it'll either pass or fail based on that logic in that contract. One other thing it can do, it can also write global and local values to the ledger. And what those mean are, I can store values associated with the smart contract. For example, I may store, if I'm doing a voting application, I can store vote totals as a global variable, for example. Then I can also store local values for anybody who options into this smart contract. These are called local state values. And so that allows me to store information about any specific user that is opted into the smart contract. So if you're voting, I could actually record who you voted for if I wanted to in local state, and it would be specific to you. In fact, in the ledger, it stores it under your account. So that's what that's what global and local state do. One of the unique things that we just added was the ability for these smart contracts to actually initiate additional transactions. These are called inner transactions. And these allow you to do things like make the smart contract do a payment transaction from within the contract, or make the smart contract transfer an asset, like an NFT or an FT. So that can all be done inside of the smart contract and can be initiated with an application transaction. So that's the high level view of what a smart contract is. But if we drill into it a little bit more, a smart contract's actually two pieces of code. We call this the approval program and the clear program. So you typically, for any smart contract, you will write two programs. The primary smart contract piece of code is actually the approval program. It's the one that's used most. We'll discuss when the clear program's used in just a minute. But so when you initiate that your code will execute. And when I talk about global and local state, one thing to keep in mind, these are key value pairs. And you can store up to 64 global key value pairs, and you can store up to 16 local values per user who's opted into the smart contract. What I was saying earlier, we use application transactions to initiate that. Well, that application type can be further subdivided into 6 subtypes. And these are the 6 subtypes that are available. Depending on which subtype you initiate, it will depend on which piece of logic actually executes. So we have the no-op call, which is probably not the best name for this, but it is think of that as the generic call to a smart contract. I just want it to run. I want to pass some parameters to it, let it evaluate its logic, and either pass or fail. That's a no-op. An opt-in transaction is a transaction. If you're going to store values per user, the users have to opt into that smart contract, and they do that with an opt-in transaction. And one thing to keep in mind is this particular opt-in subtype application subtype is not required if you're not going to store any values for locally for the user. So this is pretty much an optional one unless you're storing data. And then we have delete and update applications. Smart contracts can be updated and they can be deleted. In fact, if you don't want that to be the case, you actually have to write TEAL code to make sure that you don't allow either one of those operations to happen. Or Python, you can do it in Python as well. And then finally, we have the closeout subtype. Now, the closeout subtype is basically the opposite of an opt-in. You fire the TEAL code, and it allows you to gracefully exit out of a smart contract. Now, this may update, clear out your local state values, decrement some counters, or something like that. The problem is any of the transactions go into the approval program, and that's all the first 5 I've talked about, they can fail. So if any one of those fails, any ledger data that's been changed in the logic will be reversed, rolled back. So that's what and that presents a problem because that can actually lock someone into a contract forever. So how do you get out of the contract? Well, there's a non-graceful exit way of exiting a smart contract, and that's called using the clear application transaction. And that you still get a chance to run some logic, and you may do some cleanup code in it, but it doesn't matter if your TEAL logic passes or fails, the user will be opted out of the smart contract. But for the purposes of what you're going to see today, most of the calls that you see applications use are going to be the standard no-op application transaction. All right, smart contracts escrow. It's one of the new features that we added is the ability for smart contracts to be escrows. And what an escrow is just going to be a piece of logic that lives on the blockchain that can hold algos, which is Algorand's native currency, or it can hold what we call ASAs. ASAs are, think of similar to like an ERC20 token on Ethereum, where you create an NFT or an FT, and it can you can configure this token, deploy it, and you have your own custom token. It takes about 30 seconds to create one. Well, smart contracts can hold that as well. So the function as an escrow, the first thing you got to think about is, okay, you deploy your smart contract. And one of the things the blockchain will do, it'll return 2 things to you. The first being an Algorand address. And it'll also return a unique ID. This is called the app ID. And that app ID is how, when you send that application transaction, how you trigger a specific smart contract. Well, the Algorand address is used so you can send funds to it from some other account. So in this particular case, any other Algorand account, whether it's a multi-sig account, a normal account, they can send algos or ASAs to the smart contract. Now the smart contract holds those funds. And the only way that they can leave that smart contract is it has to pass the logic, and an inner transaction has to be initiated inside the smart contract to transfer those funds out of the smart contract. So once the funds are in the smart contract, an application transaction is triggered, the logic is executed, and then if you set up inner transactions, you can send the ASAs or the algos out of the smart contract to a recipient. And the nice thing about inner transactions, you can do up to 16 of these inside the smart contract. You can do payment transactions. You can even create a whole new NFT or FT inside the smart contract, or you can just transfer an existing one that the smart contract holds. Another thing is ASAs are very configurable. They can be configured to allow freezing and clawbacks, which freezes an asset from being transferred, or clawback where a securities company may take a token back from an account. Both of those can also be done in a smart contract. And in fact, you can even use the smart contract can also, using the logic and inner transactions, opt into additional ASAs, is what we call the Algorand standard assets. and so that's the high-level overview of how you would function as an escrow. Some other use cases for Algorand smart contracts is if you want to build a DeFi app like AMM, a lending app, or something like that, crowdfunding, voting, material tracking, lottery, seeding, basically anywhere a global variable is needed for a piece of logic deployed to blockchain, or anywhere you need to store individual values per user of your application. All these are cases where you can use an Algorand smart contract. As a case study, let's take a look at a crowdfunding application. Now, a crowdfunding application has the basic premise that says, I'm trying to raise money for a specific receiver, and if the goal is met, then we give the money to the receiver. If the goal is not met, then we give the money, allow the donators to get their money back. So the first thing you would do when you're building a crowdfunding app is you'd create an Algorand smart contract, and when you deploy it, it actually runs the logic one time when you first deploy it. So it runs the logic so you have a chance to initialize variables. Well, in this case, I may set up a set of global variables like the fund start date. When do I want this fund to be? When do I want to allow people to donate to this? Fund end date. When do I want to close it out? The goal I'm trying to get at. And then who do I want to get the funds? And then the smart contract will hold these funds. So once the smart contract's created, any number of people can come in and do a donation. And they do this by creating two transactions. One is a transaction call to the smart contract saying you want to donate. And the second is a payment transaction from the donator to the smart contract. It says, this is the money I'm donating. It's going to be any amount. So what will happen is when you do that, you'll pass, these are grouped atomically. So when you call the application smart contract can read every transaction that's submitted at the same time. So in this particular case, there's two transactions that can read all the properties of both of those. So it looks at the payment total and goes, okay, this user gave 50 algos. Well, then that particular piece of data can then be written to user storage saying how much they gave. All right, and this process will continue until to your fund end date. And at the end of the fund end date, you got two options for paying out. Well, the first one be, okay, the fund met its goal. So anybody in the system can send an application transaction to trigger the logic. And what it can do is then look and see what the fund goal was. Is there enough funds in? Did it meet that goal? And is the end date passed? If the end date's passed, then the smart contract will issue an inner transaction and send the funds to the original receiver. All right, if that's not the case, the other payout option is for the donators to recover their money. So the way they do that is any donator can then issue an application transaction saying, I want to recover my funds. So what the smart contract will do is look up how much they gave in their local storage. That's the one at the bottom, and check, and then then do an inner transaction on a payment transaction that sends that amount back to the user and decrements it from the escrow. So that's a simple high-level view of how you would use the escrow capabilities and the smart contracts to implement a crowdfunding application on Algorand. All right, so that's a high-level overview of some of the pieces. We're going to get a little bit deeper now, digging into the runtime architecture, and then we'll jump into TEAL. The runtime architecture is a little bit different, and it may be a little bit it's fairly detailed when we talk about an application transaction. Every time you issue an application transaction, you can pass a set of arguments with it. That's the argument, what we call the arguments array. So you can pass the default is 15 parameters. I think it's 16 parameters that you can pass with a application transaction. All right, that's a set of arguments. Those can be integers and byte arrays and things like that. In addition to that, we have 3 arrays that you can add to a transaction. And what are these arrays? They're called the application array, accounts array, and assets array. These are just lists of assets, accounts, and applications. And what that means is, when I told you that the smart contract can read the ledger, in order to maintain, Algorand has extremely fast throughput. In order to maintain that, what we do is any smart contract that runs, we give it a limited view of the ledger. And what's in those 3 arrays determines what in the ledger they can actually read. So the accounts array, if I want to read some account data from some other individual, then I would put their account in the accounts array. In the assets array says, if I want to read something about an NFT that's out there and use that in my logic, then I have to add that to the assets array. In the application array is, what if I want my smart contract to read another smart contract's data? Well, that's where you would put it in the applications array. You can change those arrays every time you call an application transaction. It doesn't always have to be the same ones. All the arrays that you see on the left side are all dynamic. So when I call that the runtime, we call this the AVM, first thing it does is it loads up my TEAL program, and we use a stack machine to process that TEAL program one line at a time. And as part of that, it can read in a set of global variables. It can read in all the transaction properties that were submitted at one time. But these are read-only. It can't manipulate them, but it can read those 2 pieces of data. But then it can read or write into one area we call temporary scratch, which is just a memory area that it can write to until the transactions are complete, and then that scratch goes away. So just think of it as just like temporary memory. The other thing it can do is read and write global local state key value pairs. So those are the 2 writes it can do. In addition, it can generate up to those 16 inner transactions as part of running the code. So that's a high level. And the reason I bring up these arrays because they're very important in some of the opcodes that we use inside the program to actually process them. You have to have access to certain certain things will have to be in those arrays. All right, so let's talk about the language, and this will be the fairly low level part, and then we'll work it up to hopefully be able to show a PyTEAL example as well. All right, so we have the transaction execution and approval language. That's the language, we call it TEAL. And it's a stack-based language that runs on a stack engine in the AVM, and it just uses pushes and pops off a stack. So the way the stack works is if you push something onto the stack, everything that's already there gets pushed down. If I pop a value, it comes off the stack, and everything else comes back up one layer. So everything, the pushing and popping is the most important thing to understand about the way TEAL processes a program. So it's a bytecode-based stack language. It's Turing complete. What all that means is that you can do looping and subroutines. And then its primary purpose is to return true or false. How does it determine that? Well, at the end of a program run, if you have one positive value on the top of the stack, it'll return true. If you have a 0, it will return false. The stack itself takes integers and byte arrays. Those are the only 2 things that it operates on the stack, and you'll see that when I debug and show you an example of this. But the only caveat to the returning true or false is we do have one opcode called return that will take the last value off the stack and return that value. So you don't have to worry about if you put too much stuff on the stack, you don't have to clear it all. We have over 130 opcodes. Think of opcodes as just functions that you execute on the data. The parameters passed in like arguments, and you use the opcodes to operate on that data. And then you push these and pop these off the stack is essentially all there is to it. While I'm going to show this, the one thing that's really nice that we've put a great deal of work in is the PyTEAL library. So the PyTEAL library is a library that can be used with Python, that you write your smart contract in Python, you run it through PyTEAL, and it produces the TEAL code for you. But it's always good to have a good level understanding of what's actually happening on the blockchain itself. The blockchain runs TEAL. Okay, so as a simple example, let me go through one little snippet of code. All right, this is a snippet of code from a TEAL program. And what we have here is just 3 lines. The first one uses something said, a piece of code that says TXN amount. What does that mean? Well, TXN is an opcode. It's like the function. So what it says here is I want the transaction, and I want specifically the amount field in the transaction. And then int 1000 is what we call a pseudo opcode that just loads an integer onto the top of the stack. And then greater than or equal to, it's an opcode that compares those two and either returns 1 or 0. So how this would work is the first thing the program would do is it's processing in that stack engine is it push the transaction amount to the top of the stack. The next line would then push that 1000 int on top of the stack. And then the final thing that would do is this greater than or equal to, it actually pops 2 values off the stack and pushes either a 0 or 1, depending on whether the transaction amount is greater than or equal to 1000 microalgos. Now, how do I know how much data gets pushed off and popped off and how much gets pushed on? Well, we have an opcode reference doc. What the opcode reference doc does is it tells you everything the function does. For example, in this particular case, the pops A and B off the stack. That means it's popping off it's expecting 2 integers at the top of the stack, and it'll pop both of those off. And it'll push a uint 64. And it, like I said, based upon whether A is greater than or equal to B. Now, every opcode in Algorand works this way. Some opcodes don't push anything on the stack. Some don't pop anything off the stack. So the primary way of understanding is check the opcode documentation. For example, you just saw me use the transaction one. So TXNF, that F just stands for the field that you're referencing. It is the one that actually reads the transaction data. And if I open this, and let me scroll down to the transaction one. Yeah, I think it's right after args. Yep. So this one right here, this TXNF says, okay, this is the fields that you have access to. Like I can get the sender, the fee, the first valid, the amount, things like that. So, we have over 60 properties that you can read out of a transaction. So a lot of flexibility associated with that. Well, every opcode is laid out this way. And you'll see that this one pops nothing off the stack and it pushes a variable piece of data. If I'm asking for the sender, it pushes an address onto the stack. If I'm asking for an amount, it's going to push a uint 64 onto the top of the stack. Okay, let's see if I can get that to go away. Let's see if I can go back to my presentation. All right. So that's the that's how the opcode reference documentation works. So, all right. Most of the opcodes are like I said, all opcodes function that way. Well, we do have some pseudo opcodes, and they're primarily responsible for just converting data so they can be displayed on the stack. For example, an int loads an integer, like you saw in that previous example, on the top of the stack. Well, byte takes a string. The byte opcode, pseudo opcode, takes a string and then converts it to a byte array so it can be put on the stack. So in this particular example, I'm looking at byte my string and then comparing that to the transaction application arg0 that says, give me the first argument that's passed to this smart contract. And if it's equal to my string, then I'll push a 1 on the stack. If it's not equal, I'll push a 0 on the top of the stack. And then finally, we have the address pseudo opcode that allows me to load an Algorand address on the top, the byte representation of an Algorand address on the top of the stack. And that first one that says, oh, I want to check the receiver of this transaction. Is it this address? That's all that particular piece of code does. All right, so as a way of making it a little clearer, I'm going to run a simple example. And the one thing I'll tell you is I'm running what we call Sandbox. And Sandbox is a Docker instance of an Algorand node, and I have it set up in development mode. So my transactions are very fast, and I can quickly iterate over code. All right, so and then we have documentation on how to set this up. So as part of that, I'm going to just show creating a smart contract first. All this code here is just to interact with that sandbox, and I'm copying my approval program and my clear program up to that sandbox so I can compile them and use those two pieces. As I said, every smart contract has an approval program and a clear program. In this case, the approval program is named global.teal. Okay, and here is the actual command I'm using to create the smart contract. It's called goal-app create, and I'm passing who's the creator. Then I'm passing the approval program here, which is loops and, well, that's not the right one. Let's try this one. Create state. This is the one I want to do. The approval program is just called global.teal. The clear program is called clear.teal. And what this section is, as I told you earlier, you can read and write global state or local state. Well, you have to specify how many of those you're going to do. And you can do up to 64 globals, 16 locals. So you have to specify that number when you first create the contract. It can never be changed once you create it. The only way to change it is to delete the contract and redeploy it. So you have to think long and hard about how much state you're going to use. And this is all to increase throughput. So, so that's the simple way of deploying that contract. And as I said, you can when you deploy a smart contract, you get back an address and an ID. Here, I'm just reading out that information so you can see it down here. So if I create this, I'm just running and by the way, I'm doing all this in a shell script using our Go command line tool, but every bit of this can also be done with the SDKs. Okay. All right, so deploying that contract, and it's creating it now, and here's my app ID, and it happens to be 5. That's the unique identifier that I will use in future application transactions to initiate that piece of code. Here is the address that you can send funds to and that type of thing. So as part of this, I'm going to debug that particular program. And the way I'm doing this is doing just a standard shell script again to call goal app call. And here's actually how I'm calling it. Here's my app ID, and I'm reading that in from a file because when I created it, I wrote it out to this file. All right, and then I'm passing a set of arguments. Here, I'm passing an app arg of string my arg. And because the way Go works, it passes everything as a byte array. This is just so it knows how to interpret, the Go tool knows whether you're passing an integer or string. All right, so the first argument would be my arg, and the second argument would be an integer value of 10. And I'm calling that. And in this particular case, I'm calling the app, but I'm actually dumping it out to a file so I can debug it. We have a tool called TEAL debug that allows you to run line by line in a debugger. It connects with the Chrome developer tools, and I'm going to show you that right now. All right, so here you can see we've started up the debug session. Now I just need to connect to it with Chrome. So the way you would do this is all you have to do is type in Chrome // inspect. And then you'll see this Algorand TEAL program right here. So if I click on that, it opens up a debugger, just like any standard debugger you would see. And what I can do now is I can step through the code. And the way I do that is just one line at a time, like any debugger. But the first line you see here is called Pragma version 5. All that does is tell the Algorand blockchain what version of TEAL you're using. Every new version of TEAL, we add new opcode, so you get more functionality. Well, if you're trying to use functionality and you defined your program as an early version of TEAL, those opcodes won't be available. So that's all this particular line does. So it says I'm using TEAL 5. The next thing is I'm looking at using the TXN opcode, like you saw earlier, application ID. This is going to return me that 2 or 3 or whatever the app ID was that I just created. When you first deploy your smart contract, I said the logic runs once. that value will always be 0 when the smart contract is created. So if this was the first time this logic had been called, this would be a 0. All right. Else it's going to be whatever the app ID is. And the reason that's important, if you look at my stack, this is that stack I talked about. I load that on there. My app ID was actually 5. We have Algorand allows branching. So we have 3 branching command opcodes. We have B, which just branches no matter what's on the stack. We have BZ that says branch if there's a 0 on top of the stack. And BNZ, which says branch if there's a positive value on the top of the stack. Well, since I'm using BZ here, if I had a 0 on the top of the stack, this would branch down to this label right here on line 18. And I would just load 1 onto the stack and return. That would be a successful execution. That's what happened when I deployed it the first time. But since our app ID is not 0, it's going to just skip right past that branch and go to the next line 5. All right, this is that byte pseudo opcode that you saw earlier. It's got the string counter. So you'll see here now I've loaded that onto the stack. This is an opcode called app _ global _ get. This is the opcode you use to go read those key value pairs that get stored. So what I'm saying is the key is called counter, and I want to know its value. So when I execute that, it'll return this value, and it's 0. And what I want to do is just increment it by 1. So first thing I'm going to do is push an integer 1 on top of the stack. And I'm going to add those 2 numbers using the plus opcode. That'll pop both of those off the stack and return the total. All right. Now, as I stated earlier, we have a scratch space. And so the way you load or store, manipulate the scratch space is you just use load or store. Store stores a value, load loads a value. And you can see my scratch space right up here. All right. So if I store that in the first slot, you'll see here's the first slot. I got that 1. Now, since I've got it stored, what I want to do is I got to call the opcode to write it back to the ledger. The way I do that is first thing I want to do is load up my key again, load the value I want to set it to, which is now 1, and then I use app global put, which pops both of those off the stack and doesn't push anything onto the stack. All right, you'll see my stack is now clear. So how do I return successfully? If I return right now, this smart contract will fail. But so to get around that, I just load up the current global value, which is 1, and just return now. And then that's a successful execution of the smart contract. Okay, so moving along. All right, like I said, you can access over 60 transaction properties just using that TNX opcode. And there's a whole list of them. You can just look at the table. We also have access to global variables. And these are things like, I want to know what there's a specific one called group size. It says, if I have 1 transaction, group size will be, the global value of that'll be 1. If someone submits 3 transactions at once, then it'll have the value 3. So it's a way of the TEAL program to know how many transactions got submitted at once. And you'll see how that's used in a minute. I can also get the last block number that was executed. I can also get the latest timestamp from the previous block. So so you can do time-based calculations. So the way you get access to any of these global variables is you use the global opcode, and then you say global, and then the name of the variable you're interested in. All right. Another thing you can do is I said we have 6 primary transaction types on Algorand, like payments, asset creations, asset transfers, all the different things you can do on Algorand. Well, the type enum field of the transaction object actually tells you what type it is. In this particular case, this piece of code is comparing it to APPL. So it's saying, is this particular transaction an application call? All right, so that's how you would check the transaction type. Another thing you can do is we had 6 subtypes of application transactions. You can actually check all of the the subtype of application transaction using the onCompletion field. The no-op is that generic call I told you about. And all I'm doing is comparing to see if they're equal. Okay. Another thing you can do is, let's say I don't want the only way I want a smart contract to approve something is if a user owns a specific asset. So what I can do is, I would add that asset to the assets array that you heard me talk about earlier, and I would add their account to the accounts array. And in this particular case, this int0 and int2 are just indexes into those two arrays. And then I would call asset holding get, and then the field I'm interested in, I want their balance. Well, this particular opcode returns two values. One, did it find the value? And number two, what the value was. So the first thing I want to do is just pop. I'm just using the pop command to throw away the top, the return value. This is just an example. So I'm just throwing away. Pop just takes the top thing off the stack. And so in this particular case, and then I'm comparing this to see if that's greater than or equal to 1. So this essentially checks to see if a user owns a specific asset. Another thing I can do is if they add an application to the applications array, that's essentially saying add another smart contracts app ID to an array, I can actually go read that other smart contract in the system, and I can read all its global variables. So, and you can think about this as where this one may be useful. You may have some master contract that you want a bunch of other derived values from. Think of it like almost like an Oracle if you want to use it that way, right? And then these other smart contracts can then go read that and manipulate their global data based on what's in the global data of another smart contract. We also support looping and subroutines. And when I did say the language is Turing complete, but the runtime is still constrained by what we call opcode budget. What opcode budget is, every opcode in Algorand has a numeric value that represents how CPU intensive it is. And in the opcode documentation, it'll tell you how much every one of them costs. You have up to 17 opcodes per call to a smart contract for it to run. If it doesn't complete in that time, the transaction will fail. Well, you can actually, if you group up a bunch of smart contract calls together, that opcode budget is pooled, so you can share budget across smart contract calls. Every smart contract has a size limit of 2K between the approval and clear programs. You can increase that limit to 8K, but it raises your minimum balance requirements that you have to have in your account in order to acquire that much space. And this is a way of controlling the size of the ledger. But what I have here is two things. I have a loop and I have a subroutine. And I'm not going to get into too much detail on how this works because I'm actually going to show this when running in just a second. But so we can do iterations and we can also call a subroutine. So let me show you an example of running the subroutine. All right, so let me create this loop. This stuff is getting in my way. Okay. All right, so if I go, I'm creating a loop program just like you saw me do in the previous example, where I'm deploying a smart contract. It's called loop and sub, getting back my application ID, and then getting the address. Now, I'm going to debug this same way I did before, except I'm passing an argument, int5 here. Now, what this program does, it calculates 5 factorial. That's all this program is meant to do. And it's primarily just as an example to show how things work. Oh. All right. Okay, so now I got my debug session. I'm going to go back to the inspect, click here, opens up my debug session. All right, and the first thing we're going to do here, I'm going to explain how this program works. I'm using 2 store slots. And the whole idea is I'm going to have a decrementing counter and an accumulator. Well, my decrementing counter is in store 0, and store 1 contains my accumulator. And the first iteration, I'm just going to do 5 times 4. In the second iteration, it'll have 20 in the accumulator, so I'm going to do 20 times 3. And then the third iteration, it'll be 60 times 2, and then 120 times the 4th iteration, just as an example. This is the same piece of logic you saw earlier for initializing your smart contract. We're not doing that. So the first thing I'm going to do is get my application, the argument. And right now, you see it comes in like this. It's actually because it's coming in as a byte array. So the first thing I need to do is convert that to an integer so I can actually use it in my code. So this is what this b to I does. And that will actually pop that off the stack and push on an integer value. In this case, it pushes 5. Then the dupe opcode just makes a copy of that and pushes it to the top of the stack. So now I have 2 5s. And the reason I have 2 5s, I'm going to do one of them's my accumulator and one's my decrementer. So let's store the decrementer. That's getting stored in the first slot. You can see this in the first slot, 5. Then I'm going to store the second one in my accumulator. Now, I told you there's 3 branching mechanisms. Here, I'm skipping all this code and coming down to main. So, and then I'm initializing a loop variable. So it should load a 0 on the top of the stack. What I'm going to do is I'm going to do a loop from 0 to 5 minus 1, so 0 to 4. And I'm going to call that subroutine every time. And that way I can do each one of those steps I discussed earlier. So first thing I do is call the subroutine. So it bounces up here. This is the subroutine. This is a return from subroutine. So it'll run the code from here and then return right back to where we were. So the first thing I want to do is load up what's on the, I'm going to load up what's on the decrementer, and I'm going to subtract 1 from it. So now I have a 4. All right. And then I'm going to reload up the 1 again, and I'm going to multiply those 2. So when I multiply those 2, now I have a 20. And then in the zeros, this is my initial loop counter down below. So I'm leaving that on the stack. So I'm going to store that in the 1 location. Now I have a 5 and a 20. And I'm going to load up the decrementer, and I'm going to subtract 1 from it. And now that's 4. And I'm going to store that in the 0 slot. And I'm going to return from the subroutine. Now now this is my first, 4 times 5. Now I have 20 sitting in there, right? Now I'm going to increment this main loop that we had a 0 on here, and I'm going to add that, and I'm going to dupe that because I'm going to do a compare, and it'll pop that off the stack. So I've redo it, first argument beat I, just like we saw. So 1 to 5, and I'm going to subtract 1 from that 5. So now I got 1 to 4, and I'm saying if this 1 is less than 4, then jump back up to the main loop and let's do it all again. And it'll just keep decrementing down. So another thing I can do is set breakpoints, and I'm just going to run through that so it passes all of that. And you'll see I have 1 and 120. So that my decrementer went all the way down to 1, and my total accumulator now has 120 in it. So at this point, this is what I got. I have my decrementing counter there. That was the incrementing loop counter. So I'm just going to leave that alone, and I'm going to load up the return value, which was 120. Well, in a smart contract, if you want to return a piece of logic, the way you do that is you use the log opcode. Well, the log opcode, and what it does is you get a transaction ID for every transaction you submit. If you use a log in a smart contract call, it will actually write that data into the completed transaction to the ledger field. So some other folks later can come read up that return value and use it for layer 2 type applications, whatever you want to do with it. But the issue is the log function only takes byte arrays. So the first thing I need to do is convert that integer back to a byte array so I can log it out. So first thing, that's what I've done here is convert that to a byte array. And then I'm going to log that, which will pop that off the stack. And the only thing I'm left with is my incrementing counter from my main loop. Now, at this point, since I have a positive value on the top of the stack, I can return. And everything worked fine. So that's a successful completion of that smart contract call. All right. So going back into the smart contract demo, what I told you earlier that you can do up to 16 inner transactions. If you're sending out whoever you're sending the transaction to from an inner transaction, they must be in the accounts array. What you use to send transactions is the ITNX opcodes. So I have ITNX begin that says I'm getting ready to initiate a transaction, and then submit actually submits the transaction. Everything you see in between those is just setting fields. For example, I want to set I use ITNX underbar field opcode to set the type enum, which is the type of transaction I want to send. So in here I'm saying load int pay, and I want to set the type enum field to that. So I'm saying, okay, this is a payment transaction. Then I load 5,000 on the stack, and I set that to the field amount. So I'm saying send 5,000 micro algos. Now, this particular application is just a somewhat goofy, contrived example that says, I want to create an escrow, fund that escrow, and anybody sends a transaction to the smart contract saying pay me, the contract will automatically send them 5,000 micro algos. So whoever sends the transaction is going to be the receiver of this inner transaction. And then I do an ITNX submit. I'm going to show you what that looks like in Pyteal so you can get an idea. Well, what is Pyteal? Well, Pyteal is a Python library, as I stated earlier. And what it does is you can write smart contracts with code like what you see here on the left. Don't worry too much about what's in the code yet, because I'm going to show you an example of it. But what it allows you to do, it allows you to write it in a language that's a lot easier to understand and decipher. And you run that, when you run that piece of PyTEAL, it'll produce the TEAL for you. So this produced that. And so, and like I said, we're constantly making vast improvements to make PyTEAL even easier to use. So PyTEAL has a whole set of documentation. When you get the link to the presentation, you'll have a link to the documentation. But everything in PyTEAL is documented for all like an opcode on TEAL has a representation in PyTEAL. So you'll be able to look at all the TEAL opcodes using PyTEAL. So definitely worth reading. Let me show you what a PyTEAL demo looks like, an example of it. All right, so here is, I got a simple escrow, this one I just talked about, the one that says pay me 5,000 microalgos. Well, the way this program is built is we have a main, and then we have a couple conditions in here, and I'll explain these in a minute. This first thing here, all this does is it's kind of like the main program, and it calls the PyTEAL library compile TEAL, and this app command calls my function up here to give me back the PyTEAL. And then by compiling that, it'll produce the TEAL for me. And all I'm doing is printing that out. The mode application, while I've been discussing mainly smart contracts, all the stuff you're seeing here can be used for what we call smart signatures. So when you specify which one it's being used for, mode.application is smart contract, mode.signature is smart signature. And then finally, the version equals 5 is the version of TEAL that you're using. So in this particular case, this app function, it has two primary areas. And when they use what we call PyTEAL expressions, this is the condition expression. And what this means is it says, if this is true, if this condition is true, do this. If this condition is true, do this. So the first condition is just on the creation. When you saw me check to see if an app ID was equal to 0, then you know that's the actual creation of the smart contract, not just a normal execution of it. So here I'm saying, oh, if we're creating the smart contract for the first time, just go ahead and approve it. What approve does is loads a 1 on the top of the stack and immediately returns. All right. So every other condition, and if no condition meets the case in a condition expression, the transaction will fail. So in this particular case, I'm saying, okay, if it's a no-op application transaction, then I want to return whatever this function generates. All right, so this function right here is using a sequence expression, which is similar to a condition expression, except that what it does things in order. So for example, it does this line first, then it'll do the next line, and so on. If any one of those lines fail, it'll fail the transaction. So this particular first case says assert and this. This is the TXN opcode, if you want to think about it that way. And this is the way you get application arguments. So I'm saying, give me the first application argument to this program and comparing it to the string pay me. If that returns a 0, the assert will automatically fail the smart contract call. If it passes this, then we know the string was pay me. So the next thing I can do is I can use when you're building an inner transaction in PyTEAL, you use the inner transaction builder. And you begin one by using the .begin, and you submit it with the .submit. Everything in this middle section is just setting the fields for the transaction. So use the set fields command. I'm setting type payment, setting 5,000 microalgos, and setting the receiver of the inner transaction to the sender of the application transaction. And that's pretty much all there is to that piece of PyTEAL. All right, and the way I run that, but you can see the import from PyTEAL right there. The way I can run that is I can just run Python simple escrow, and you'll see this generates the TEAL out here for me. All right, same thing, similar to what we saw earlier. You'll see some of the labels will be auto-generated, like this label here. But I can debug that in very similar fashion that you saw earlier when it's deployed to the smart contract. So I'm going to do a shell script says simple escrow debug shell. Did I spell that wrong? Oh, I know what I did wrong. Okay. Simple escrow debug. Gotcha. Okay. All right, so it's deploying to the same way you saw me doing earlier, deploying it to our sandbox environment. If I go back over to inspect, now what you see here is the actual TEAL that got generated and deployed. Is right here. And like I said, everything you've seen me do, you can do with the SDKs and instead of just Go. So here, same logic for initialization, checking to see if it's been created or not. And then next thing I'm checking on the stack is the on completion. That's I'm trying to see if it's a no-op call. Does it equal no-op? So I compare those two, and they are both in fact 0. So equals would puts a 1 on top of the stack. Here's that BNZ I told you about earlier. So I'm jumping down to handle loop. Otherwise, I would load an int 0 on the stack and return, which would be a failure. So stepping down to that, next I'm checking the first application argument. Does that and loading byte pay me on there? Are those two equal? If they are, here's my assert that you saw. If I assert here, it should pass it by because I have a 1 on top of the stack. And then I'm going to do my transaction just like you saw earlier. So the first thing I do is tell the system, the blockchain, that I want to do a payment transaction. I want to set the type enum field to pay. I load 5,000 microalgos on the stack, set the field for amount, and you notice it pops those values off the stack as soon as you set them. Set the receiver to the sender of the application transaction, and then I submit it. If that transaction fails, the smart contract will fail. But since it didn't fail, I can load 1 on the top of the stack because I have nothing on the stack, so I need to return a positive value. I load an in on the top of the stack, and then I return. Okay. So that's a high-level overview of TEAL, Pyteal. And what I would say is, I think the next session that you guys are going to get is next week is a platform called Reach. What does Reach do? Reach is a much higher level laying framework that allows complete applications to be built. It handles integration with front ends, and it also handles all the integration with the blockchain. If you don't want to write a smart contract at all, you can write it in Reach, and Reach automatically generates all the smart contracts for you. And it also mathematically formally verifies all your smart contracts. The primary thing is it's written in a JavaScript-like language where you just you primarily focus on the business logic in the code, and you write all the business logic and let the framework generate all the smart contracts for you. That'll be the next one coming up, and I hope you attend it if you're interested in smart contracts and dApps on Algorand. If you want a copy of this presentation, here's a link for it. You can take a screenshot of it if you want real quick. And then finally, the last thing I want to say is we have our Discord server. Please join if you got any questions about anything to do with Algorand. You'll get plenty of answers there. We have our dev portal where we completely document almost everything in the system. There's forums if you want to ask questions in the forum, and there's the GitHub for Algorand. And the last thing I'll say is every two weeks we do a developer office hours, and we cover hot projects on Algorand, new technology pieces that we're launching, showing demos, and I do a bunch of things like that. And so if you're interested in learning more about Algorand, please join the developer office hours. And I can take some questions if we have time.
Thank you so much, Jason, for having today's session. It was really, really helpful. And thanks so much to Russ for supporting you throughout. And I think I can see like Russ is sharing the links in the chat for everyone. Thanks so much for that. And thanks so much to our moderator, Eileen, for doing the moderation. Now, if you have any questions, please feel free to write them down in the chat or in the Q&A box. And Jason and Russ will be able to answer them.
Great job, Jason.
Thanks, Russ.
Thoroughly enjoyed that.
And like I said, if you join the Discord channel, we have a very active Discord channel that we can help you get through any application you want to build.
And I posted that link in the chat window as well. So yeah, that's a great resource.
So I would also like to remind that the 4th session of this whole series will be on December 9th at 1 p.m. Eastern. And the session will cover developing on Algorand with Reach, which Jason also mentioned. And next, we will have a meet and greet session in the blockchain track, and the time and date is still to be decided.
Yeah, there was one question on how does Algorand handle updating applications. So if you saw there was 6 subtypes of application transactions. One of them is an update, and you can update the contract. And what do is you issue that contract and you supply the updated program, and it will redeploy those. That's essentially all it takes to update an application. Now in TEAL, you can actually check for the subtype and say, if you're trying to update it and I don't want to allow it, just load 0 on top of the stack and return. And that will deny that capability.
Awesome. Please feel free to ask more questions in the chat.
I do want to say it's been a real pleasure presenting to you, and I want to thank everybody for attending.
Pleasure is all ours, Jason and Russ and everyone from Algorand. It has been such a great pleasure to having you all for all these consecutive sessions. I remember the first session was conducted by Russ in our Connect Forward conference, and I was also the host for that one, Russ. And it was a very well attended session. So
yeah, and I do want to mention that we are just coming off of a very great conference, Decipher. We had a lot of great content there, and if you keep your eyes on our YouTube channel, youtube.com/Algorand, those sessions should be posted in a day or 2, and so that would be another great resource for everybody here in attendance.
Awesome.
Mm-hmm.
So could you please write down the name in the chat for our attendees so that they can...
Yeah, I'll do that right now. Let me get that in here.
Thank you.
Okay, that will be the link to keep your eyes on right there.
Great. So I think we are almost at the end of time, and if there are no more questions, then we can wrap up today's session. Before we end this call, I would like to mention, like, you can follow us in womenwhocode.com/blockchain. That's the website for blockchain track. You can be a member of blockchain track. You can also email at blockchain@womenwhocode.com, and you can also follow blockchain track in all these social platforms in Twitter, Facebook, Instagram, and LinkedIn. And with that, I'd like to end today's session. Again, thank you to Jason, Ross, and our moderator, Aline, for having the talk with us today. And thanks to all the attendees for joining us. Any last thoughts from Jason and Ross?
No, just thanks for the opportunity. We really appreciate it.
Yep.
Thank you so much. Have a great day ahead, all of you.
Great weekend, everybody. Bye-bye.
Bye-bye.
Bye.